que, después yo les voy a circular una hoja de papel para que se anoten por el tema de los certificados de asistencia. Así que en cuanto a cosas prácticas, y después de la sesión de práctica, a las 4, va a haber un pequeño café para, si quieren interactuar con los profesores después de la clase. Así que, bueno, para empezar quisiera, simplemente para no robarles más tiempo, contextualizar un poco cuál fue mi motivación para invitar al doctor Laerte y a Vitor a La Plata para traer este curso de Machine Learning. Yo comencé a colaborar con la gente involucrada en la colaboración SPLAS en el año 2018 y en el 2020 se organizó aquí en el observatorio la 9ª lápiz. Con la gente de SPLAS logramos traer 14 investigadores de Brasil para dictar las clases de esa escuela, y muchas de las cosas que se mostraron ahí fueron, a mi criterio, voy a hablar por mí, es una impresión completamente personal, es una astronomía con la que no estamos en contacto todavía acá en La Plata y que se viene en los próximos años y está ocurriendo. Estoy hablando de la fotometría multibanda y lo que implica trabajar también con grandes volúmenes de datos, que es lo que producen estos relevamientos multibanda. Y aparejado a esa cantidad de datos que se generan, están todas las técnicas asociadas a ese tratamiento o esa astronomía de contexto de Big Data. Entonces, ya en el 2020 con la lápiz, ellos comenzaron a traer estas técnicas de Machine Learning y de análisis de grandes volúmenes de datos, y tuvimos la posibilidad este año de conseguir una plaza de profesor visitante, que es con la que nos visita el doctor Laerte Sodré. El doctor Laerte Sodré, es un placer recibirlo y le agradezco enormemente que esté acá. Él ha hecho su máster y su doctorado en la Universidad de San Pablo, ha sido postdoc del Observatorio Real de Greenwich, actualmente es full professor en el Instituto de Astronomía, Geofísica y Ciencias de la Atmósfera de la Universidad de San Pablo, del cual también ha sido director. Es miembro de numerosas colaboraciones como JPLAS, JPAS, SPLAS, y también es coordinador de la participación a través de FAPES de Brasil en lo que es la construcción del gran telescopio magallánico, uno de los grandes telescopios de 30 metros que se encuentran actualmente en construcción. Es un experto, un pionero, creo yo, en la aplicación de técnicas de Machine Learning en el área de astronomía, así que muchos de ustedes me han manifestado, bueno, vengo de oyente, simplemente no importa. Yo creo que lo importante que tienen que llevarse de este curso es al menos conocer que estas técnicas se están aplicando en astronomía y que son técnicas que plantean grandes posibilidades a futuro. Así que, Laerte, muchísimas gracias por haber venido, un placer tenerte.
Un placer es mío.
Así que, adelante.
Gracias, Analia. Bien, voy a me mover para allá, que es más fácil. Ustedes pueden me interromper en cualquier momento y hablar en la lengua de ustedes, porque mi portuñol creo que no es tan malo.
No, la clase va a ser en inglés, así que, pero nos podemos comunicar en portuñol.
Okay, this is a very brief abstract of a course of 6 months that I usually do in São Paulo, okay? We will have 4 classes. The first one today, I will very briefly pass over statistical methods. This is a bit crazy, but I will try to present to you the main topics in statistics that you should know, not by my course, but for you, to deal with data analysis. The second class will be a presentation of the general concepts of machine learning. In the third class, we will discuss problems of regression and classification using machine learning. And finally, in the fourth class, we will do with deep learning. The idea is to have a very practical course. So, for each topic, we will develop practical activities, and the responsible for it will be Vitor Cernic, my master student who came with me, because he understands Python and I don't understand anything of Python. And as you might know, Python is one of the most important languages today to deal with data analysis. My bias is towards R. R is wonderful, but I think that's better for you to learn Python than R. The best is to know both, but since we don't have too much time, you should learn Python. Okay. Today I will talk about data, probabilities, descriptive statistics, and inference. These are very broad topics. I could spend 6 months talking about them. But, you know, I will just present a general overview of these issues, and Vitor will develop some of them in exercises in Python. Okay. Everything in science runs around data. Data is essential. And in a time where many scientific values are being contested, it's important to all the time reassure what is indeed science. You know, our conclusions in science are not based in opinions, but are based in facts and or evidences. And you know, we do measurements or observations, and we get data. Due to the nature of the data, they are naturally, implicitly, and explicitly, they have errors, uncertainties, and this is what we need to take into account when to deal with data. What is important for us in science is that data brings information, and you will see at the right an example of a data space. Okay, this is a three-color diagram where we can see clouds of points. Each point is a datum. Data is the plural of datum, and I think that the concept of data space is one of the most important that you should know. Okay, when we have data, whatever the kind of data we have, we can think about it as a point in a data space. For example, if we have a photometry in 4 bands, G, R, I, Z, for example, from the Sloan Digital Sky Survey. We can have a sample of millions of or hundreds of thousands of galaxies or stars, and we can imagine in this example a data space of 4 dimensions, one corresponding to each magnitude, G, R, I, or Z. And what is interesting is that the data is not randomly distributed in the data space, but on the contrary, the data space has a structure. And what we need to do, what we want to do, is to find the structure in the data space with the techniques that we will discuss today and the next days. Okay. Data is essential to science, as we have seen. I like the definition of science that was proposed by Galileo. Science is what translated to our nowadays language. Science is a database, the description of the nature using the language of mathematics. And what we try to do as scientists is to describe or interpret the nature through data modeling. An essential point is that data have a statistical nature. And this occurs because the measurements or observations have uncertainties and errors. And we need to incorporate these uncertainties and the errors in our modeling of the nature. To do that, we need probability. Probability theory is the natural way to quantify uncertainty. So most of what I will talk today regards probability. And an essential point associated to it is that we can consider data as random variables. So we assume that a given datum is a sample of a probability distribution. So if we consider, for example, a data set D comprised by measurements xi, we assume implicitly that this data is drawn from a certain probability distribution, P of x. We might know or not P, but anyway, we assume that the data comes from a probability distribution. This is the basic assumption in data science. The data can be regarded as a sample of a probability distribution. So we need probability theory to do data analysis. So, for example, in this, we have here a probability distribution of a given random variable x, and here we have a sample of this probability distribution. I think that you are all used to random numbers between 0 and 1 that often we need to do simulations. This is a sample not of a uniform distribution, but of, say, a gamma distribution or something like that. And in the same way that we can use Monte Carlo techniques to obtain samples of a uniform probability distribution, we can do the same for any probability distribution. So samples are obtained from probability distributions. Probabilities. Probabilities in general are numbers between 0 and 1. There is a big discussion, a big polemic between the statisticians about the nature of the probabilities that I will try to avoid here. I will want just to mention that there are two basic ways to look at the nature of probabilities. The most classical way is called frequentist, and considers probabilities as a measure of the frequency of events in several experiments or in an ensemble of statistically similar systems. So in the frequentist view, probabilities are measure of frequencies. On the other side, we have the Bayesian view that has nothing to do with frequency. In the Bayesian view, probabilities are a measure of the degree of belief or plausibility of an event. It's interesting to mention that among the hard sciences, astronomy was one of the first sciences to bring the Bayesian vision to the scene. The reason is that the frequentist view is not good for us astronomers. We don't have many universes to do frequentist analysis. We have just one universe. We are unable to play with planets like we can play with dice. So the Bayesian view is much more natural for scientists and for astronomers in particular. So I will adopt essentially a Bayesian point of view, but you don't need to worry about that, because in practice many of the results that we will obtain are the same, using one technique or the other. I will talk talk a bit more about it later. Well, there are many different types of probability distributions. They can be continuous or discrete. They can be univariate or multivariate. It can be of the population or of the sample. The sample is derived from a given probability distribution of a population. Well, an interesting, maybe the most difficult problem that we need to deal with in data analysis is with the nature of the data. Because, you know, everyone who already worked with data in astronomy knows that we have missing values, we have bad values, we have contamination, we have many things that we need to take into account. And one of the ways to approach the data, to know it better, is through what we call descriptive statistics. Statistics is any number that somewhat summarizes an aspect of the data. For example, the mean of the data. So, what the descriptive statistic does is to provide a brief description of what is the probability distribution function, or PDF, of the data. So we can define expected values for a given function fx, for example. In this way, the expected value of f is this integral of f times the probability distribution. This is the mean. This is for a continuous distribution, and here is for a discrete distribution. We can define several types of descriptive statistics. In general, for measurements of location, width, or form. Examples of the statistics of location are, for example, the mean, the median, and the mode. For width, we have the standard deviation, interquartile distance, and the mean or median absolute deviation. We have also statistics of form, skewness, and kurtosis. And important concept also is of the one of the robust statistics. Robust statistics are a kind of statistics that is less sensitive to outliers. For example, the median is more robust than the mean for location measurement. The same with the interquartile distance. I will talk a bit about it later. So, the mean of a population is defined in this way. Okay, here I have a distribution. I suspect that this distribution is of, it could be anything, magnitudes, distance modulus, etc. And we have several measurements of location in this plot. We have in blue the mode. The mode is the most probable value. You can imagine that the mode is not the very good measurement of location, because maybe you have already had this experience of doing histograms, and you know that the mode of the histogram depends on the number of beans that you are using. So the mode, although interesting, is not too much used. Has a measurement of location. Much more common are the mode, are the mean, and the median. And another important quantity that is shown here by the black lines is the quartile distance. This is the first quartile distance. The points at the left of this line represents 25% of the number of points, and the points to the right of the magenta line represents 25% of the points in this extreme. Okay, measurements of the width of a distribution. We can define the variance of a population has the expected value of the variable minus its mean, or this is for say population or for a sample. If I have any measurements of a quantity, we can obtain the variance of the sample this way. The mean or median absolute deviation is defined in this way. Instead of using the square, as we do with the variance, we use the modulus of the difference between the random variable and the mean or the median. And here is the same for the sample. And sometimes we multiply this for values, a constant value, in this case with this number, so that if we have a Gaussian distribution, the MAD will be equal to the standard deviation or the square root of the variance. So this is a number that we might have in mind, because you know, if you use, say, Python or R or any language and computes the MAD, in general, this factor is already incorporated in the equation. So if you will compute it for, say, a Gaussian, you don't need it to, or any other distribution function, you don't need to apply this factor because it's already incorporated in the algorithm. Okay? Well, the standard deviation, that is the most common of the width measurements of a distribution, is the square root of the variance. Another important quantity I have already mentioned is the interquantile distance. The quantile function, it gives the value of x for which we have that the area under the distribution is a given number. So if the area of distribution corresponds to 0.25, this corresponds to the first quartile. If it corresponds to the 0.5, it is the median, and 0.75 corresponds to the right quartile in this region of the curve. So the quartiles, they divide the probability distribution in regions of well-defined probabilities. The most used is are these values here, but in principle you can use any value of p to define the quartiles, okay? In this case specific, they divide the PDF in 4 areas. This area, this area, this area, and the other one. A number that I think is useful for probability distributions in general is this quantity here, that in the case of a Gaussian distribution, this quantity is exactly equivalent to the standard deviation. But with this number here, we generalize this interquartile distance for any distribution. Another important descriptive statistics are the skewness and kurtosis. The skewness measures this type of distortion. It's a momentum of the probability distribution over order 3, and is defined in this way. Sometimes you see this definition or for continuous quantities or for discrete quantities, but Anyway, we have many distributions in astronomy, physics, and in the nature in general that have or positive or negative skewness, and so the skewness is also an important quantity. The other quantity is kurtosis. Unfortunately, the colors I have used in this plot is not very good, but here you can see is the Gaussian. A Gaussian, by definition, has no kurtosis. The kurtosis is defined by the force moment of the probability distribution. If we have a more peaked distribution than the Gaussian, this distribution, for example, has a positive kurtosis. Otherwise, it will have a negative kurtosis. So, and notice the following. In this definition, I am subtracting this value 3. This happens because the kurtosis of a Gaussian is 3. But you should be aware that this depends on the algorithm that is implemented in the language you are using. Some languages include this -3 in the definition of the kurtosis and the others not. I don't know what Python does. Maybe Vitor can tell us later. And for example, I have here a given probability distribution, and I computed the skewness. It's almost 1, very close to the skewness. Very far away from the skewness of a Gaussian. Look here. For a Gaussian, this skewness would be 0. And the more pointed than a Gaussian, the skewness is positive. Okay. One of the most important things that we do in data analysis is data modeling. We have a data set, and we want to fit a model to this data set. In general, the model has parameters. I will call the parameters by the W. For example, I can write a model for a given data D has y is a function of a given x given the parameters W. Here is an important concept of machine learning. If W is a continuous variable, we have a problem of regression. If y is a discrete variable, we have classification. So the distinction between regression and classification, the first distinction, is about the nature of the dependent variable, whether continuous or discrete. In general, we can do 3 main types of inference. Parameter estimation. We want to determine the value of W that best fit the model, the data. Errors. We want to have estimates of the errors. How confident should we be of our estimate? And another important approach is regarding hypothesis testing or model comparison. For example, if you have 2 models, are they consistent with the data? What model to prefer, model 1 or model 2? This is done by hypothesis testing or model comparison. And again, when we talk about frequentist and Bayesian approach regarding data modeling, there appears the first important difference for us. In general, the frequentist approach, we determine the values of the parameters W through the maximum likelihood model. We and the maximum likelihood solution is in general a point solution. We don't have a distribution of values of W. We have just the best value of W. At the same time, probably you are all aware of the p-values. This is the way that the frequentist approach does model comparison. They compare the values of quantities with the values expected for a given distribution, and they obtain a p-value from this comparison. And the errors estimates are present in general as confidence intervals. So I have a variable h naught that is equal to 73 plus or minus 0.1, for example. The Bayesian approach has a different way to see the determination of parameters. We don't adopt a single value for a parameter, but we represent the probability distribution function of the parameters. So, in the case of the frequencies approach, the solution for the best parameter is the value of the best, the value that maximizes the likelihood. I will talk about likelihood soon. In the case of the Bayesian approach, the best solution is the probability distribution function of the parameters. Also, we don't use p-values in Bayesian approach. We compare different models using a quantity that we call evidence. And the errors are somewhat similar to confidence intervals, but are measured directly from the PDF, and they are called credibility intervals. In order to know what is likelihood, what is evidence, etc., we need to see a bit of the theory of probabilities and the Bayes theorem. Okay. Let's consider first what are conditional probabilities. In general, probabilities are conditional. And by that I mean that they depend or can depend of other variables. So, if I write p of x given y, I read it as probability of x given y. So, if y is true, this gives the probability of x. It measures the plausibility of x given y. For example, a Gaussian distribution. I can write using this notation. If you appoint, I am describing a given sample or model with a Gaussian distribution, the probability of x given the Gaussian parameters mu and sigma is given by the Gaussian distribution. So you can see that the probability of x is conditional to the values of the mean and the standard deviation of the Gaussian. From this distribution, this definition of conditional probabilities leads us to the concept of independent variables that are very useful in science. If pdx given y doesn't depend of y, and the pdy doesn't depend of x, we say that x and y are independent. Their conditional variables does not depend of the other variable. Another thing that we have in theory of probabilities, joint probabilities, pdx and y. pdx and y measure the joint probability of x and y, the probability that x and y are true together. Of course, we can also add conditional probabilities to joint probabilities. So, pdx and y given z means the joint probability of x and y given z. Okay? Well, given all these things, we can define the two fundamental rules of probabilities. The sum rule, the integral of the probability of x dx is equal 1, or for discrete probability distributions, the sum of the p in several p's is equal 1, and the product rule, pdx and y is pdx given y times pdy. These rules, the product rule is somewhat intuitive. If you think you see it, I want to know what is the probability of x and y being true. This is equal to the probability of x being true if y is true times the probability that y is true. You can think about it later. From this rule, we define what we call the Bayes theorem. We can write the p dx and y the way I have done, p dx given y times p dy, and reversely, since p dx and y is equal to p dy and x, has p dy given x times p dx. Combining these things, we can write this expression. P dy given x is p dx given y times p dy over p dx. This is called the Bayes theorem. It was proposed firstly by Bayes, this guy here, in 1740, but was popularized by Laplace in 1774. Actually, this is not the true Bayes. Nobody knows who his guy is, but in every book you see that he is Bayes, but he's Bayes. But this is not true, because if he indeed was Bayes, he would not be present with this hair, but with something like Laplace, because at this epoch people used the perucas. I don't remember the name right now. Okay, looking at this, certainly all of you have heard about the Bayes theorem. Looking at this expression, it's difficult to see why this is relevant for data analysis. But now I will show to you. If instead of thinking about abstract random variables like x and y, think about that. If we are considering a model M that we are applying to a given data set D, which has parameters W, okay? We can write, using the Bayes theorem, exactly the same thing. The probability of the parameters given the data and the model with this expression here. That's exactly a translation of what we have above. The probability of the data given the parameters and the model times the probability of the parameters given the model divided by the probability of the data given the model. The expression at the denominator here is the normalizing factor. You can see that it is the integral of the numerator, and that this is done to assure that the probability is normalized, is properly normalized. Well, in the context of data science, each of these terms have different names. So the first term here, the probability of the parameters given the data and the model, is what we call the posterior distribution, or a posteriori probability distribution of W. That's why I have said that in Bayesian analysis, we don't give just a number for a given parameter, but we give the probability distribution. This other term here is the likelihood, that probably you already know. The chi-square, for example, is linked to the likelihood of a distribution with Gaussian errors. The likelihood measures the probability of the data given the parameters W of the model. The last term here is the prior of W, is the probability a priori of W, is what we know about W independently of the data. And finally, the term here, the normalization term in the denominator, is called the evidence of the data, or marginal likelihood. I will not have time to talk too much about the Bayes theorem, data analysis, etc., but we will try to do some exercise along the course, okay? let's see how we do statistical inference. When we use a point that I think that's important for you to take notes is that the Bayes theorem provides a complete recipe for doing data analysis. This is not true for the frequentist approach. The frequentist approach has lots of rules, whereas using the Bayes theorem, everything is logically deduced. Okay? For example, we have here this expression that I have just present to you for the Bayes theorem, and how we do Bayesian parameter estimation. Look, the denominator doesn't, W, the parameters, doesn't appear here in the denominator. So we can obtain the posterior distribution of the parameters simply writing the product of the likelihood with the prior of the parameters. And this is interesting. So it is interesting to note that the the evidence doesn't enter in parameter estimation. The best estimate in the case of the Bayes theorem, as I mentioned, is the posterior probability distribution. And it requires the likelihood and the prior. From the, say, let's suppose that this is the posterior of a given distribution. You can see that from this distribution, I can estimate many types of different errors. I can estimate the probability of that the points are around a given area of the parameter value, things like that. And we can also, using the Bayes theorem, arrive at what we call the Bayesian model comparison. That is very different from the p-values used for statistical model comparison in the frequentist approach. It's relatively easy to show from the Bayes theorem that we can compare two models, model 1 and model 2, given the data, by the ratio of their evidences times the product of the ratio of their priors. In general, we don't have different priors for the models. I mean, if you are starting a data analysis, you can think that model 1 has good, has model 2. So this ratio is 1. And in this case, assuming that, we can conclude that the probability, the relative probability of models is the relative probability of the evidences of each models. This is a very powerful result of the Bayesian approach. Okay, but most of us uses all the time the frequentist approach and the maximum likelihood method. Let me explain a bit more. In the frequentist approach, the likelihood that we just saw in the Bayesian approach is considered as a function of the parameters, okay? So I will write L has a function of W. This is the likelihood. For example, let's consider again our Gaussian models. Let's suppose that we have measurements X, Y with errors sigma, and we assume that we have a given model that I would describe by the function f. It could be, say, a straight line or like in this case or whatever. That depends of the parameters, okay? In the case of a straight line, we have two parameters, W1 and W2, that are the inclination and the zero value of the model. Okay, if we are assuming Gaussian errors, the probability of a given datum y is a Gaussian. Is given by the value, the measure value of y, minus the expected value computed from the function divided by the square of the error. this is a Gaussian model for the errors of a measurement. In this case, the likelihood of the data set, assuming that the measurements are independent, is just the product of all the individual probabilities. And this can be written as the exponential of minus 1/2 of chi-square, where chi-square is given by this quantity. So I suspect that all of you already know about chi-square, but my point here is to show the connection, um, say, with the error model and with the how it is linked to the Bayesian likelihood. So, in the case of maximum likelihood approach, the best solution is the one that maximizes the likelihood or minimizes this chi-square here. You know, I have mentioned that in the Bayesian estimation, besides the likelihood that is exactly the same that we use in the frequentist approach, we also need a prior, okay? The prior measures our what we know about the parameters before doing anything. In general, we don't assume too much. We can use, for example, uniform priors. In this case, the value of the maximum likelihood solution is the same value that maximizes the posterior PDF. So the maximum of the posterior is equal to the solution that maximizes the likelihood. So this is why, in general, many people says that there's not much difference between Bayesian and the frequentist analysis. But this is not true. This is only true when the prior is uniform. Okay. Well, how we define errors or uncertainties in maximum likelihood? In general, we obtain confidence intervals by measuring the width using derivatives, for example, of the likelihood. Or we can use data resampling, like the bootstrap method, where we resample the data we have many times. Each time we estimate the value of the parameters, and then we estimate the uncertainties, bias, and the confidence intervals um, using the bootstrap distributions. For example, I have here um, a data set with several data points, and I can bootstrap these data points. I mean, we can select randomly the any points from this distribution with repetition, estimate the values of A and B of this straight line, and plot them here. And here the distribution we obtain with bootstrap, and then we can estimate, say, confidence intervals, bias, etc. The quality of fitting in the case of maximum likelihood is usually obtained with the reduced chi-square. The reduced chi-square is defined as the maximum of the maximum likelihood, the parameters that maximize the likelihood, the chi-square for this value, divided by the number of points minus the number of parameters. This is the reduced chi-square. And we expect that this number is about 1 for a good fitting. Okay. As I mentioned, in the case of a frequentist approach, the we use frequently what we call hypothesis testing to estimate the p-values. And I'm mentioning this here because during the activities you'll probably run some statistical test, and it will appear a number p there. What this value p means, this is what I will explain to you now. suppose that we have a given measurement, say, theta equal 2.2. And I want to know whether it is consistent with a model for which theta 0 is equal to 0 plus or minus 1. In the frequentist approach, we define what we call the null hypothesis. We assume that we know the distribution of theta, and we call it p d theta. And if we know p d theta, we can also know its cumulative distribution function. The cumulative distribution function is the integral up to a given value of theta of p d theta. Okay, in this example, so let's assume that p d theta is a Gaussian, and here means normal distribution, that is a synonym of Gaussian. So we have a normal distribution of parameter theta with mean 0 and standard deviation 1. I am representing this expression by this probability distribution. Our observation corresponds to a value 2.2. So here I'm representing this probability distribution of the null hypothesis, and here is the value 2.2, and in red here you can see this area here. This is the p-value. The p-value measures this area here in the case of this example. This p-value is the probability of obtaining a result has stream, has the observation, given the null hypothesis. Okay, f d theta here is the cumulative distribution, is the integral from minus infinite, in this case up to this point, 2.2. Okay, so in this case the p-value is 0.01. In general, the smallest the p-value, the better the confidence in that the null hypothesis is not correct. Model comparison. Suppose that we have here a set of points, and we don't know if it is best fitted, say, by a parabola, a polynomial of degree 2, or by a polynomial of degree 20, say. Let's suppose that we have n points, and we have two models, m and m line, and the values of the maximum likelihood obtained for each model. Of course, if a model has much more parameters than the other, its likelihood probably will be much larger, okay? Because it will fit better the point. But this doesn't mean that this is necessarily the best model. There are some frequentist ways to compare different models. And I'm showing to you here the big Bayesian information criterion that, despite the name, is not a Bayesian procedure, but a frequentist one. Peak of a given model is defined this way: K, that which is the number of the parameters of the model times the Neperian logarithm of the number of points minus 2 times the natural logarithm of the likelihood. Note that, and we want to that the peak is small. The smaller, the better in the case of comparison of models. Note that this term, if the model has a large number of parameters, it will increase the value of peak. On the other side, if the model has a lot of parameters in general, this likelihood will be larger. So this peak, it penalizes the number of parameters that a model has, and at the same time compares the likelihood of the models. The first term then penalizes model complexity, number of parameters, while the second penalizes the quality of fitting. And we compare models by comparing their peaks. So in this case, for example, the parabola is a model that is much better than this polynomial of degree 8 that overfits the data. Okay, maybe we can use big during the lecture. Okay, now I will transfer the to Vitor. Vitor will talk about Python, and today he will talk. He will give to you an introduction to Python. We will do a presentation of descriptive statistics with Python, and we will also present Python tools. Vitor, that's for you.
Lo voy a presentar a Víctor, que hoy no lo presenté. Te conocen. Bueno, Víctor es muy joven. Víctor tiene tan solo 24 años y él está haciendo el máster.
Make things readable. So you can mix both text cells, such as the ones that you're seeing, with code cells, such as the one down here. Okay, so most of you raised your hands on when I asked you about Python, but you can install Python and Jupyter notebooks in your own machines. So if you want to install Python, you can run it, install it through the Anaconda package, which is the easiest way to do. But if you are want to run Jupyter notebooks, I think you can also install them through Anaconda, if I'm not mistaken. But if you run everything on Jupyter, in Google Colab, which is the website we're running here, everything is remote. You don't need to install anything. You just need to have an access to internet, and you can run your code. So also in Python, we have what we call libraries. So libraries are a way to try to gather functions and other codes from other people that probably have gone through the same thing as you want to do. For example, if you want a function to calculate the mean, you don't need to write the function down. You have a library that has inside of this library a function called mean to calculate the mean or median or whatever statistics you want. We'll be using a lot of libraries in the future. So basically, most of the machine learning code that we'll be using in the last few classes will be through libraries, the TensorFlow or Keras libraries. All right. So, also, if you want to import libraries, if you want to run the functions, use the functions that have it in the library, you just write down import and the library you want. So running Python codes in Jupyter Notebook is fairly easy. You just click on the. This will give you a warning because it is not a notebook created by Google. It's created by me, Vitor Cernic, and you can trust me. This will not corrupt your computer. And you can just click on the arrow. You will run your code after connecting, which is the thing over here on the top. Okay, so you ran your code and printed hello world. And you can do this for every other cell. Some results are stored because it makes visualization easier. So when I ran this notebook a couple weeks ago, it stored the results. But you can just click again and you run again. You see you will get the same results. And for printing things, you can either write down like this. So for example, print and a variable, or you can simply type the name of the variable. So for example, if you write A, you print it right here. And also one of the things about Colab itself is that if you change this notebook, you will not save the changes. So you can see over here at the top that it cannot save changes because this is a notebook that was not created by you. So if you want to copy this notebook, you can go here on File, and I think there is a Save a Copy in Drive, and you can then edit and put whatever code you want. All right. So also, if you have any questions, please stop me. But I'll try to go over this quickly since we have another class to to talk about. So in Python, we have different objects. So for example, we have integers, floats, which are like real numbers. We have strings for text. We have booleans for true or false. We have lists. We have arrays. We have a lot of different types of objects. And you can all see a type of an object by writing this built-in function called type. And in Python, it's fairly different, for example, from the C language or Fortran, which you need to initialize a variable. In Python, you don't need to do that. You can just go ahead and, for example, what I've done over here, which is a equal to, I didn't specify that, for example, the a is an integer. You can just start writing it down, and Python will understand. One of the things you can do, which is like the first code that everyone sees in Python, is using Python as a calculator. So if you use some functions from the math library, which is a built-in Python library, which comes when you install Python itself, we can do a lot of calculations. So for example, 2 plus 2, or if you want to do some more complex calculus, we can use exponentiate, we can use get the value of pi, we can calculate logarithms, we can calculate the Neperian logarithm of some other values, or square root. Any other thing you want to do, you can do calculations. You usually use the math library, and you can do a lot of that fairly easily using these blocks over here. This is just to basically present to you how the Python formatting works, or how the codes are structured. And one other thing that is fairly important in Python is lists. So lists are usually when we want to, for example, write down a variable. So for example, x equals 10 or y equals -2. This is storing just a single value, a single number. So if you want to store a number of numbers, we can use lists, which are basically arrays. So I think if most of you programmed, most of you are already familiar with this concept. If not in Python, in any other language, we have some kind of array or some kind of list. And in Python, it's no different. So we do have, for example, I want to create a list that gets the number 0, 1, 2, 3, 4. So I just write down with the brackets. And if I want to add a number on the list, I can write append, which will put the number at the 5, for example, at the end of the list. And if you want to access elements of the list, we can just use these brackets over here. So for example, my list 1 will obtain the second number of the list, because the list starts at 0, so 0 is the first, 1 is the second. And we'll see that the second number of the list is actually 1. If you want to obtain a range of numbers, for example, I want to obtain the elements number 2 to number 4, I can use the double points to obtain, for example, from the second element up to the fourth element. So it will always exclude the last one. So it's going to be 1, 2, and 3. So 1, 2, and 3. And we can also, one of the useful things that we can do in Python is obtaining the length of the list. So for example, in this case, we have 0, 1, 2, 3, 4, 5. So we have 6 elements. All right, so we will not be using lists at all. We actually will be using NumPy arrays, which are much faster than lists for most of the things we want to do. And but I will be presenting this in the tools notebook. So I think this is one of the notebooks that Analia passed you. This is basically gathering all of the tools that we'll be using in the future. But I'll go through it later. One of the things that we have in Python, as well as many other languages, is loops and ifs. So conditions and loopings. So if you want to create a loop, we can either do that by using the while. So for example, while x minus is less than 4, and it will execute the code below, which, for example, while x minus than 4, we will print x, and then we will add 1 to the value of x. Whiles are not used that much in Python. We usually use for. So that is much more common when seeing a Python code. For basically is a way to say, for example, for I in this list. So what we try to do is it is going to execute the code below that many times, and each time you change the value of I, the variable I, to be the next one. So for example, the first time it executes this code, so double I is equal I plus Y. So in the first case, for example, it will enter as is0. So 0 plus 0 is equal 0, and 2 times I is 0. So 2 times I is 0. The next time it executes this code, it's going to go to the next variable, and so on and so forth. And you can, of course, mix and share, mix and match these conditions and this looping. So you can create a code, for example, that has the just to talk about the if else, but this is one of the conditioning ways to write in Python. So you can use statements, which is, for example, if x is greater than 3, then execute this code, or else execute this code. And I think this is fairly easy to visualize and understand the way it works. But you can, of course, mix and match loops and conditions. So for example, you inside a loop, you can include a condition. So for I in 0, 1, 2, 3, 4, if I is greater than 2, print this is greater than 2, or else it is smaller than or equal to 2. So 0 is smaller than 2, 1 is smaller than 2 or equal to 2, and so on. One last thing that I want to talk about is functions in Python. So even though we will be using a lot of external libraries, you can create your own functions. So this is very useful when you want to make things easier to read in your code, or you want to somehow pass a function as a variable. I will talk about this, I think, in the class number 1. But it's just to understand that we have this possibility. So for example, if you want to define the double function, which is it takes an argument x and returns a value of 2 times x. To call this function, we just write its name down and give its arguments. So for example, double 3 is equal to 6. So 2 times 3 is equal to 6. That's the idea. Let's see what I was thinking. Oh yeah. One of the things in Python is that since it's what we call an object-oriented language, we we end up with some interesting things, such as, for example, let's say that you have a function that takes in a variable and a list, and it changes the value of the variable inside the function, and it changes a value of the list inside the function. And what will happen outside of the function? Usually when we write down code, we want everything to be constrained. So for example, if we change the variable number inside the function, we want the variable outside of the function to not change. And it's the same with the list, but let's see if that's what happens. So in the case of Python, if we, for example, let's give it some initial numbers. So x equals 0 and the list is 1, 2, and 3. So you print down here that x equals 0 and y is equal 1, 2, and 3. If we go through, if you apply this function, so the change function that I define here, it will change the value of x to 4, and the my list, the second element of the list, will be changed to minus 999. And if you see after the outside of the function, when I print those variables again, I see that the value of x isn't changed, but the list, the second element, is changed. So basically, when you are dealing with lists or arrays, Python changes the value of that of the elements when you go through a function, because it doesn't. What it actually does is that for each element over here, is stored in a space in the memory. So in the memory space of the computer, there is a specific memory allocated to each one of those. And when it changes inside the function, you actually change those memory spaces. In the case of single variables, that's not what happens. So it's just something to be aware of. So I think it covers most of the what I want to say about Python itself. I think if most of you are familiar with Python, I actually wrote a. Let me just refresh this page, because I actually wrote a an exercise over here. Okay, so there you go. So if you want to know basically how Python works, and just see if you're familiar with it, you can do this exercise. You're not obligated to do this exercise, but if you want to, it's just a very simple code. Create a new Jupyter code cell, which you can do that by clicking on code over here. Import the math library, create a new functions that takes a number and outputs the square roots of the number, and print the results for numbers 1, 4, 5, and -20. And yeah, I think that covers most of the things that, like the general concepts of Python. And we have some. I left here some reference, so the Intro to Python tutorial from Data Camp, and Learn Python from the Kaggle websites. So one of the things that I mentioned somewhere around here is that there is a what we call a tools library, so or notebook, which is basically this one. So I try to compile a list of useful libraries. So NumPy, Matplotlib, Seaborn, Scikit-learn, and Pandas, and SciPy, which I think will be useful throughout the course. And basically, this notebook is trying to show you how each one of them works. Trying to like very briefly describe what is NumPy, how do you deal with arrays, what it's trying to do, and give you some useful links on how to get other information. So let's say, for example, that you are you want to know more about how to work with NumPy, you can go through these links. There's the same for Matplotlib, for Seaborn, which is a graphing library, for Scikit-learn, which we'll be using, we will be analyzing a lot of data with. Pandas, which is a library that describes data frames, which we'll be using a lot in the future. So most of the machine learning problems we will be using data frames instead of arrays. And yeah, I think that's it. And the SciPy library, which is basically an ecosystem that tries to gather a lot of other libraries and contains a lot of useful functions. So I think that covers most of it, because I don't want to go into too much detail in this tools notebook, because I want to talk about the class 1, basically what Laerte told us. Laerte, can you open the abrir a aula 1 em algum lugar, eu acho que eu mandei para você. Depois eu tenho e-mail que eu mandei para Maria também. Ah, não, 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 o notebook. O notebook. Eu mandei para você. Okay, so all right, so I'll try to give you a practical introduction about descriptive statistics and what Laerte talked about today. So just a quick introduction to Google Colab. If you click on the three dashed lines, sorry, the 3 lines here on the left, you can see a table of contents, so you can easily go to whatever section you want. But I'll try to talk about descriptive statistics in Python, histograms and plots, parameter estimation, uncertainty. Sorry, I won't be talking about uncertainty estimation. I forgot to take that out. But I'll talk about p-value testing. I'll just mention a little bit about uncertainty estimation. There is nothing code-like. So starting with descriptive statistics. So Laerte talked about a few statistics on the class, but I'll talk about then in a visual way. So most of you know, I think all of you probably know average, median, standard deviation. These are very common metrics, very common statistics, and they try to evaluate a kind of some kind of data set. So if you have some amount of data using these metrics, you basically you're trying to summarize the data. You have trying to get a grasp of the data in just a single number. But so if you want to see that how that works in Python, let's start by creating some random data. So for example, let's generate 80 Gaussian inference. So for that, I'm going to use the NumPy library, which is described in the tools notebook. And from that library, I'm going to use the random sublibrary, and I'm going to import a few functions. So I'm going to import the normal function and the seed function. The seed is basically a way to set how the random numbers are going to work. So if I give a number for the seed, for example, 1, 2, 3, 4, it doesn't matter how many times you run this notebook or which day of the week or which time of the day, is always going to give you the same output as I presented down here. So if let's create some random Gaussian inferences. So we need a value of the median, so the center of the Gaussian, which we're going to set as 0, and we're going to use a sigma, the standard deviation of the Gaussian, which will be 0.5. How to get the some amount of inferences, so some amount of Gaussian data, we use this normal function. So we basically give the function the center of the Gaussian, the mean, the standard deviation, and the amount of points we want. So in this case, let's say that we want some 80 points. This is going to return an array of random variables. So I'll store this in a random list variable. A good way to visualize this is using a histogram. So a good way to visualize one-dimensional data, so in this case we have a number of inferences, is to use a histogram. So here we will be using, so this is the first time I'm showing you how to use the matplotlib library, so basically plotting graphs, and using the Seaborn libraries as well. So they are both very similar. Matplotlib is the basis of most Python plots. Seaborn is a way to, it's basically a higher level graphing, which gives us access to a lot of interesting things. So for example, let's say that I want to plot a figure, and I set the figure size, for example, 10 and 5. So 10 in length and 5 in height. And I want to plot a histogram. So I use the Seaborn function called histplot. I'll give the data that I want. I'll tell it how many bins that I want. And I'll give this argument, KDE, which is the kernel density estimation. Basically, it's the argument that tries to fit this line over here, this smooth line, which we will be talking in the next class. So in the next class, I'll show you how to calculate this line and without using necessarily Seaborn. We give you a more in-depth idea of how to estimate the density of a function. So you can see that, for example, for 80 inferences, we see that it should look like Gaussian, but I mean, it has some strange things. For example, the edges of the data are not that good, so it is not looking actually like a Gaussian. There are some things that we could improve. So in the idea that, so what I already talked about before is that when we take a sample from a distribution, if we take the, oh, sorry, let me just show you the metrics, but of this distribution. So the mean, we can calculate those metrics. So for example, the mean, the standard deviation, the skewness of the Gaussian, and the kurtosis of the Gaussian, by using some built-in functions. So from the statistics library, you can calculate the mean and the standard deviation. From the scipy.stats library, you can actually calculate the skewness and the kurtosis of the distribution. And those gives you some interesting numbers. So for example, the mean of the Gaussian is 0.02, the standard deviation is 0.49, and so on. And we can see that, for example, the mean is tending towards 0, is very close to 0, and the standard deviation is very close to 0.5, which are the original values. And as Laerte told us before, the skewness of a random of a Gaussian such as this should be 0, and the kurtosis of the Gaussian should be 0. The kurtosis is calculated by subtracting the number 3. So it's what we call a Fisher calculation. So it should tend towards 0 for a Gaussian. And we can see that even though those values are close to 0, maybe they should be closer. So if we take a lot of, technically, if we take more samples of this probability distribution, as we get more data, the distribution of the sample should be similar, should be tending towards the distribution of the original distribution. So if we take a lot of more samples from the Gaussian, the distribution of the sample should be similar to the distribution of the Gaussian. So let's see if that works in practice. So let's sample, instead of 80 values, we will sample 100,000 values. And in Python, you can actually use the underscore symbol just to separate the numbers in a. So for example, if I want to write 100,000, I can just use an underscore in the middle just to make things easier to visualize. But it changes absolutely nothing in the code. So let's calculate some metrics of this data set, this new normal distribution, and let's plot. And we can see that compared to the previous distribution, it is much more smooth. So the KD estimation follows the Gaussian much more. We can see that the mean, the standard deviation, the skewness are much closer to what it should be. So the mean should be 0, the standard deviation is 0.5, and so on. So the values are much closer to what they should be. So yeah, that's a good sign. And I think this covers most of the descriptive statistics that I wanted to talk about. As you get more data, you can basically fit your probability distribution. So the next thing that I want to talk about is parameters estimation. So this is one of the things that I think most of us, I mean, at least in Brazil, where we come from, most of our labs, when we are in grad school, we actually have to do some kind of parameter estimation, basically fitting a line through some point, and it never works. So I'll try to give you an example of doing this, not by using some built-in function, but by actually coding the likelihood as Laerte presented. So the frequencies approach to parameter estimation by maximizing the likelihood. And even though this is particular for one example that I'm going to show, which is going to fit a linear regression, basically the idea throughout all of machine learning is going to be some kind of parameter estimation by minimizing not just the likelihood, but some kind of cost function. So even though this is going to be a very simple example, this creates a basis for everything we will see in the next 3 classes about machine learning itself. So let's say that we want to do some parameter estimation, and let's generate some data. So let's find. Sorry, this is going to be fitting a line through some kind of data. So let's create the data itself. So again, I will set the seed which will be for reproducibility. And let's create a function. So I'll define a function as it takes an argument x, and it returns 2 times x plus 1. So basically, f of x is equal to 2 times x plus 1. I'll try to zoom in so you can actually see the note, because it's quite hard to read. If you go through Python library and search online, you see that maximizing things are quite hard, but minimizing things are quite easy. So Python does have a minimize function, which I'll be describing later. But what we will be doing is, instead of maximizing the likelihood, we will be minimizing the negative likelihood, which is basically the same thing, it's just writing it the other way. So let's define, and this is actually pretty common in whatever type of probability type of likelihood, or whatever you want to do with likelihoods. You always see a neg likelihood somewhere in the code instead of the likelihood itself. So let's define the likelihood function. Sorry, the negative likelihood function. So it will take some. The way that we want to do is to we want to pass this through a minimize function, which I will be describing later. But to basically make it so that it's readable for the function minimize, I need to input some parameters, which will be the estimations, so the parameters that we actually want to know. And now we're going to give it some x data and some y data, which is the same ones that I plotted in this plot over here, the x data and the y data. In this case, we need to define the parameters, which will be called the angular coefficients, the linear coefficients, and the Gaussian standard deviation, which is basically the error of the data itself. And then we need to define the linear function, the function that we want to fit. So in this case, we want to fit a linear function, so it will be the angular coefficient times the data plus the value of the linear coefficients. And the likelihood will be centered at 0, which is that's why I'm going to instead of using simply the y value as the center, or sorry, the f of x as the center, I'm going to use the y minus f of x as the center, just to shift the Gaussian towards 0. And what we want to do is calculate this sum over here. So we want to calculate the sum of basically what is type over here. So the sum of the log of the PDFs, the likelihood distributions. And again, we will be located at 0. And after you type all this down, we want to return the negative likelihood, so basically minus L. And this is the function that needs to be minimized. So even though it is quite complicated to look at it first and try to understand everything that is going on, we can go to, if you look at this a lot of times, there is very little you need to change if you want to apply this to other cases, which is going to be the exercise that I'm going to leave you with. So I'm going to talk about that later. But we need to minimize this function. So we're going to use a minimize function called minimize from the scipy.optimize library. This minimize is going to use a gradient algorithm. So it basically tries to calculate the derivatives of the function and tries to follow the derivatives in some kind of way to find the minimum of the function. And the output of the function is a type called optimize result, which has a lot of information that we want to know. So like some things like the parameters, or the number of iterations, for example, if it converge or not. And since I think this basically describes how the minimize function works. Looking at it, I will go through it step by step. I think it will be much clearer. And since the Gaussian error, so the standard deviation of the errors cannot be a negative number, since the standard deviation cannot be a negative number, we need to actually give that constraint to the minimize function. so it doesn't fall into some kind of minimum or global minimum, or sorry, some local minimum or whatever you want to. Basically, we need to type that the sigma cannot be negative. So what we want to do here is, for example, let's say that we want to call the minimize function. First, we need to give the function that needs to be minimized, so the neg likelihood. Then we need to give some initial data for the parameters. So let's say, for example, that the linear coefficient, sorry, the angular coefficient is 3, the linear coefficient is 2, and the sigma of the errors is 1. And then we need to give the function some data. So in this case, we're going to give the x and y's that we plotted over here. And then we need to describe the constraints of the function, what it needs to check to make sure that it doesn't gives us anything that is absurd. So in this case, we need to, even though this is typed quite in a like not good way, but basically we're giving it a dictionary that's going to try to, we need to give it some kind of something to look out for. So in this case, we're going to give the x2 parameter. So here the x2 parameter is the sigma of the errors, which we don't want to be smaller than 0. And we need to tell it how to constrain this number, which is the type, what I'm trying to say by type. And in this case, I'm going to give these arguments called inec, so inequality, which basically restricts it to be over 0. And I didn't take this out of my head. It's all described in the scipy optimize.minimize page. So let me open the pages so you can all see. So if you open the function page and the documentation, you can actually see every single argument. So you have the function, you have the initial values, you have the arguments, and somewhere here you have the constraints. And if you go out and look for the constraints, you have a lot of constraints over here. And so you have a lot of the types, which can be equality or inequality, and then at the end you have some documentation explaining each one of them. Basically, what I'm trying to say is that each one of these parameters I did not take out of my head. These values over here are all, I always look at the documentation first to see what I should do. Okay, so what we want to do is run this code. So if I run this code over here, it will give me a optimize, what I call an optimized results model, which will be describing both the parameters and if it converge or not and everything else. So let's see if this works. So let's calculate a line that goes through the best fit. So let's find the angular coefficient as being the x0 of this model, which is the same that I described over here in the parameters. So the parameter 0 will be the x0 of the output result. And so we have some angular coefficient, some linear coefficient, and then we will create some points, and then we will fit a line over with those points, given those parameters. And then when you plot the data, you actually see that it fits very well. The results are actually pretty similar to the ones that we described before. So the angular coefficient is similar to 2, and the linear coefficient is near 1. And just so we can see the other parameters of the model, here is the x, so the parameters, and we can see that optimization terminated successfully, so it converged, and the number of iterations that it had to converge was 25. And yeah, I think that this describes mostly of the parameter estimation. And just so you are aware, there is a Python function called linear regression. So you don't actually need, every time you need to fit a line, you don't actually need to create the maximum likelihood function, sorry, the likelihood function, and minimize the negative likelihood and etc. You can actually use some simpler functions. I just wanted to do this to show you what Python is capable of and the ideas behind what we usually do with a single function. All right, so and the last thing that I quickly want to go through is the p-value test, which Laerte described earlier. So basically, the p-value is a test, is a frequentist way to evaluate a statistical result. So to see this in action, and I think this is better grasped with an example. Let's say that the average height of a baseball player is 1.95 meters, plus or minus 0.08 meters. Someone that has the height of 1.8 meters tells you that they are a basketball player. Based on a degree of confidence that you need to decide, is there a way to see if probably the person is or is not lying? So first, we need to define a null hypothesis. So let's say that the null hypothesis is the age is 0, which is that the person is in fact a basketball player. So let's assume that the person is a basketball player, and let's see if that hypothesis holds true. Now we can perform a p-value test to see if the hypothesis holds up. So in this case, we will use the cumulative distribution function, which basically, as Laerte pointed out, I don't have the. Let's see if I can open his slides, which are here. So just to show you that the when we want to compute the where is the p-value here. So this graph over here is basically what we want to calculate. So basically, we have a distribution of the basketball players. So it is a mean of 1.95 and a standard deviation of 0.08. And somewhere along this probability distribution falls the person that told me, oh yeah, I have 1.80 meters and I am a basketball player. So we want to compute the probability of this function being a of this x string being true. So of the data actually falling into this extreme, at least in this extreme. So in this case, we will use the cumulative distribution function, which calculates those basically the integral in this tail of the Gaussian. And so this function, the CDF, the cumulative distribution, comes from the norm function from the scipy.stats library. And you can quickly Google, for example, cumulative distribution function in Python, and the first result will be this one. And so to calculate the p-value will be basically we input the measurement that we had. So in this case, 1.80, and the mean of the distribution itself, and the error, the range, so sorry, the standard deviation of the distribution, in this case 0.08, and then we just call this, and we obtain the what we call the p-value, which is in this case will be the CDF. And then when we print the p-value, I just want to show you that Python has a way of formatting strings. So if you want, for example, to show only the 3 numbers after the dot, you can the decimal points, you can use this kind of wording here. So basically the brackets, and use the dot format after, and place your values inside this dot format function. So in this case, the p-value was 3.04%. So with a confidence level of 5%, the null hypothesis is rejected. So we cannot say that this person is in fact a basketball player. So based on the data we have available, that the mean average basketball player is 1.5 meters, plus or minus 0.08, this hypothesis is rejected. So this is probably not true. And yeah, I think that's so. Even though we don't usually use p-values in statistics, sorry, in astronomy, it's very hard to find a use for p-value in astronomy. But I wanted to show you just because it's a very important thing outside of the scope of astronomy, and I think a lot of people can take advantage of this kind of test in other things, not just astronomy itself. Okay, so I'll give you a exercise. So let me just quickly go over it. So Cepheids, which I don't know if you're familiar with, but they are pulsating stars, which means that their luminosity varies through time. So if you take a picture right now or after 5 minutes, their luminosity of the star will change. Let's say that someone, the famous Harlow Chaplin, was observing one of these stars for some time and managed to write down a table, in a table there both their luminosity and the time as they progressed. So as time progressed, the luminosity also changed. And Shapley is pretty sure that this data is actually following some kind of pattern. So he gives you this data and asks you to calculate the mean of the luminosity, which is going to use the descriptive analysis statistics that I showed before. Plot the time versus luminosity data, and fit a function that you think best suits the data. So after you plot the data, you see some kind of pattern. So you just need to fit this function to this data. And I try to make it as easy as possible, just to like give you some blank spaces, so to make this easier for everyone. And so first you need to calculate the mean, then plot the data, then feed the function. And to feed this function, just because we showed you before how to do this with the negative likelihood, I'm going to leave you with this kind of approach. You can use any other approach that you feel makes sense. And yeah, I think and here's an extra well, exercise if you want to. So basically just plot the new fitted function that you fitted above. And yeah, so I think this is most of what I want to talk about. Here are some like some references. If you want to know more, you can head to these links, show you how to plot and represent data. It's a very interesting course. This from Coursera will show you a lot on how to work with matplotlib, with Seaborn, and some other things. Here is a article from QuakeCon talking about the maximum likelihood estimation step by step, and applied data science with data Python specialization from Coursera. And yeah, I think that's it.
Hola. Questions for Victor? Claudia.
Thank you, Victor. I have a question. When you define the likelihood and then you minimize it, it's not clear to me why you minimize or you try to optimize also the sigma, which is the error. Normally, when we want to estimate parameters, we estimate somehow we define or we search for some likelihood function, and normally the error would be the covariance matrix, or in this case, just the dispersion as the estimation for sigma. I never seen the minimization of the likelihood to obtain the parameters and to obtain at the same time the error. Yes. So I want to ask you, in this case, you are just like minimizing altogether to have an estimation of the sigma? Because that was unclear to me.
Do you mean by are you asking about these specific things, so the constraints, or the generality of the minimizing the errors of the?
I see that there you have like the negative likelihood function that you define.
Oh, yeah.
You have the two parameters, which are the angle and the ordinate, yes, the two angular coefficient and linear coefficient, and then you have also the sigma, which is the Gaussian standard deviation, which is your error there in this simple expression for the likelihood. Normally, one would, from the data, one would estimate the dispersion, or the variance and the dispersion, and say, well, my sigma is this and the likelihood, and I would just optimize to get the two parameters, M and B. But when you minimize here, when you optimize with this function, below,
Mhm.
you also get a value for sigma. It's like
Yes.
you're getting the 2 parameter plus an estimation of the error.
Yeah.
This is something that I don't.
It's because if we don't try to change the sigma and we give us a fixed value for the sigma, I noticed that in this case the the fits will actually not converge. So I don't know exactly the exactness of how does it work, but I noticed that if you don't give the sigma itself, the fitting will not converge in this case. So I think it has something to do with how the PDF is being calculated or the minimize function is being defined. But yeah, we actually need to input the sigma as a value, as a parameter.
I don't agree with you.
Okay.
No, she's correct. The parameters of the model are A and B. Sigma depends of the distribution that you're assuming. You're assuming a Gaussian, so sigma is a parameter of the Gaussian. But you don't need it to fit sigma to fit a straight line, you know. No, you don't need it. I can assure you. Since I don't understand Python, I don't understand exactly what is written there, but I'm certain that you can fit a line estimating only A and B. You don't need sigma at all. Why sigma appears, I have no idea, but I can write the same program in R, that's my preferred language, and I use just a function, linear model, where I write y has a function of x, and the parameters are A and B for a linear model. I will revise this problem with him to see what happened, because
Okay.
look, mm-hmm. Yeah, no, I agree with you. When we talk about parameter estimation, in this case, we want to obtain A and B. If he wants to obtain sigma also, he's going beyond parameter estimation. He's fitting the probability distribution. Uh, um, he's making a model where the data can be modeled by a Gaussian with errors of typical weight sigma. So he included sigma as a parameter in the model. But this is not the usual way we do linear regression. But I think that I'm understanding what you did. He included sigma as a parameter in the model, you know. So you have A, B, and sigma has the parameters, where sigma is a measurement of the errors. But you don't need to do that. He's extending, I would say, the linear model. Yeah, assuming that the standard deviation is a constant, he is estimating the standard deviation. But probably it should be the same that you obtain by fitting the line and computing the standard deviation. Probably it is the same. Yeah. Yes, yes. But anyway, he's assuming that it is constant because, yeah. I will revise the code with him and tomorrow I'll let you know. More questions?
So in your lecture, Laerte, when you talked about the model comparison, at some point you said that the prior of the model one, you were talking about a comparison model, and you said, that the probability of the model one and probability of model two usually are considered the same, so this ratio of priors for the models are 1. But I was thinking about what would be the space, the statistical, the statistical space for defining the probability of this model. What would be P of M1 and P of M2? When you're thinking of different models, it's difficult to me to imagine what would be this probability of a model when you have myriad of models, possible models.
Hello, hello. Hello? Yes, look, by model, suppose that we are considering, say, fitting a straight line or a parabola or a polynomial of degree 8. What is the difference? What is the probability of a linear model compared to a probability of a polynomial of degree 8? I don't know. You know. You don't know too. That's why we in general assume that is the same. Because what happens is the following. If you adopt the probability laws, you can write the probability of whatever you want, including the probabilities of a model. But we don't know a priori probability of a model. That's why I'm saying that in the Bayesian approach, in general, the prior of the models, that is exactly pi P of M1 or P of M2, we don't know. And so we assume that's the same. Said with other words, we don't have a priori any preference for a model compared to the other. We will only decide by comparing their evidences, the evidence of the data given the model. That is what happens with the Bayesian approach. We don't know, as you have said, the probability of a model. In this case, there are cases when you can use it. But the best way to see it is the following. Suppose you have a model with k parameters and another model with k plus 1 parameter. That is very often a situation that we find in science. You can show, you can, all the time you assume, as far as I know, that the probability of the model, the most complex model compared to the less complex model is 1, because a priori you don't know what model is the best. So we don't use this ratio in the model estimation. You only use the evidence. Look, this works very well. because you don't know a priori whether the straight line or the parabola is the best model. You know? No, this is a problem, but this is the great problem with the Bayesian method, the priors. But
maybe my question was a point to just the nature of as when you introduce the concept of the data and the space in which or the parameter and the space in which this parameter lives, and I think about the models, I think about in which parameter, in which space this model live, in which I could define a probability, and it's very difficult for me to imagine a space in which to define all the possible models, and there we could define the probability of a model, yes, because models can be whatever you could imagine.
You are right. But that's why we don't use this probability.
Okay.
That's the point. We don't know. So we assume they are the same. It's the easiest solution.
Questions? More questions? Okay, if there are not, I invite you to go downstairs and enjoy the coffee. And thanks a lot, Laerte, Vitor, wonderful lectures.